Welcome to The Explainer. Today, we're diving into something pretty wild. How does a computer actually learn to recognize what's in a picture? The secret lies inside a special kind of AI called a convolutional neural network, or CNN. Let's break it down.
So let's start with a question that seems super simple on the surface. We look at this picture and boom, our brains instantly know it's a cat. Easy, right? Well, for a computer, it is anything but simple. So how does it get there?
Because here's the thing, a computer doesn't see a cat. It doesn't see fluff or whiskers or ears. It sees this, a giant grid of numbers. Each number just represents the brightness of a single pixel. A tiny 28 by 28 pixel image is a grid of 784 numbers. How on earth do you get cat from that?
Okay, so you might be thinking, why not just feed all those numbers into a standard AI? Well, the problem is a traditional network would take that grid and just flatten it. It turns it into one long, single-file line of numbers. And in that process, all the spatial information, which pixels are next to which, is completely lost. It's like trying to solve a jigsaw puzzle after you've tossed all the pieces in a blender. It just doesn't work.
So to solve this puzzle, we need a specialized tool. And that's where the convolutional neural network comes into play. Its secret weapon, the absolute key to making this work, is something called a filter.
I want you to think of a filter, sometimes it's called a kernel, as a tiny little detective with a magnifying glass. It's just a small grid of numbers, maybe 3 by 3, and its entire job is to slide across the image looking for one and only one specific clue, like a vertical line or a little curve or a certain texture. And you can have a whole team of these little detectives. You've got one that's an expert at finding vertical edges. Another one is a pro at spotting horizontal lines. You can even have filters that blur the image or the exact opposite and sharpen it. Each one is a specialist, totally focused on finding its single pattern.
So what happens when one of these filters scans the image? It produces something called a feature map. And you can think of this map as the detective's final report. It's basically a new image that lights up everywhere the filter found its specific pattern. It's a map of all the clues.
Okay, finding these basic patterns is a fantastic start, but now the network has like dozens of these feature maps. It's a lot of information. The next big job is to cut through all that noise and find the real signal.
And it does this with a really elegant, repeatable process. We call it a CNN block, and it's got 3 main steps. First is convolution, that's applying the filters. Second is activation, to clean up the maps. And third is pooling, to shrink them down. And this whole block can be stacked again and again.
Let's zoom in on that second step, activation. So after we find all these features, the network runs a special function on them. A really popular one is called reload. All it does, really, is go through the feature map and throw away any negative numbers. The effect is that it makes the important stuff, the positive signals, pop even more. It's like cranking up the contrast on the most important clues. But wait a second, even after that, these feature maps are still gigantic. We're still dealing with a mountain of data. So the big question is, how does the network shrink everything down without throwing away the good stuff?
The answer is super clever. It's called pooling. Basically, the network takes a small chunk of the map, like a little 2 by 2 square, and boils it down to just one number. Max pooling is really common. It just looks at that square and keeps the biggest number, the strongest signal. Average pooling takes the average instead, which is great for getting the general vibe of a texture. Either way, the result is a much smaller, more manageable map.
So the image gets put through this whole pipeline, convolution, activation, pooling, not just once, but multiple times. And each time it goes through, it's getting less like raw pixels and more like a rich, abstract map of features. So now, let's see how this all comes together for the final decision.
All right, let's trace the entire path from start to finish. We begin with our image. It hits the first CNN block, where maybe 32 filters are looking for really simple things, basic edges, curves. Then, the output of that goes into a second block, this time with 64 filters, which start combining those simple lines into more complex shapes. You know, things that might be an eye or an ear. After a few rounds of this, the final high-level feature maps are flattened out into one long list. And that list is finally fed to a standard neural network that makes the final call, yep, that's a cat.
Now what's really cool is that none of this is set in stone. A developer can go in and tweak all sorts of things, like how many filters to use or how big they are, and it can totally change how well the AI performs. It's all about finding that perfect balance.
Let's take the number of filters, for instance. The more filters you have, the more patterns the network can learn, right? Which usually means better accuracy. But there's a catch. Every single filter you add makes the network more complex, and it takes way longer to train. If you go overboard, like with 128 filters here, you risk overfitting. That's where the model basically just memorizes the training pictures instead of actually learning what a cat looks like in general.
So, is there a magic number? Well, not exactly, but the source material we're looking at suggests there's a definite sweet spot for a lot of common problems, and it's right around here, between 32 and 64 filters. That seems to be the best bang for your buck, balancing power and efficiency.
And it's not just the number of filters. Their size matters a ton too. Think of it this way. Small 3x3 filters are like having a magnifying glass. They're amazing for spotting tiny details, the texture of fur, a sharp edge. But larger filters, like a 7x7, are more like stepping back to see the big picture. They're better for capturing the overall shape of an object. And you know what? The best networks usually use a mix of both.
And all of this leads to a really, really important point. A CNN is a phenomenal pattern-matching machine. It gets incredibly good at finding the statistical links between a bunch of pixels and the word cat. But, and this is a big but, it doesn't understand what a cat is. It doesn't know about being fluffy or purring or chasing laser pointers. It's not about meaning. It's all about the math and the patterns in the numbers.
And that leaves us with a really mind-bending thought to end on. If a CNN is just a master at finding patterns in a grid, what else could it see? It's not just about images. You can turn sound waves into a grid, or financial data, or even language. Anything that can be represented as a structured grid is a whole new world just waiting for a CNN to come in and find its hidden patterns.